Hello. So in this next set of screencasts, what we're going to do is go into one mechanism in specific detail and look at all the subtleties of that mechanism that are hidden away. In our basic rules for mechanism, we presented simple rules that allow us to understand electron flow in molecules, but the precise details of how we apply those can vary a little bit, and it allows us to expand on those simple rules to get a more complete mechanistic understanding. So what you'll be doing in your degree is visiting each kind of reactivity and each type of functional group and learning more about them. And in this course, we're going to learn more about nucleophilic substitution reactions. And first of all, we're going to consider a mechanism that's referred to as the SN2 mechanism. And we need to understand what each of those terms means before we look at what the mechanism is. The S in SN2 stands for substitution. The N in SN2 stands for nucleophilic. And the 2 in SN2 stands for bimolecular. And what does bimolecular mean? It means there are two molecules in the rate determining step. Two molecules in the rate determining step. So let's think about this mechanism then. It is, in fact, the mechanism that we've already considered for nucleophilic substitution. It follows our basic rules. We have a nucleophile. Where do we put our pen on the paper? We put it where the negative charge is. The negative charge moves towards the carbon because it's delta positive, and the electrons want to end up on the delta negative electron withdrawing X atom. So the nucleophile attacks this molecule and kicks out the leaving group. It does that all in one step. So it goes through this situation where the nucleophile is half attached and the X is half disattached. And it's worth noting that if we draw a bond like this, a dashed line, see how it's different to this wedged bond? That shows stereochemistry. Drawing a bond like this means we're making or breaking a bond. It's like a half bond. And what this is in the middle here, this is a transition state. And it's important to note with a transition state, with these half bonds in it, it's a transient species. It cannot be isolated. So it cannot be isolated. Okay? And this symbol here is a symbol that we use to mean transition state. So we can define the rate of this reaction. And this is a bimolecular process. We need the nucleophile to react with this molecule here. So the rate equals a rate constant K times the concentration of the nucleophile times the concentration of CH3X. There are two different species in the rate determining step. If we look at the energy profile for this reaction, you see that reactants go to products via a transition state, and this transition state is a maximum in energy. When we've half broken and half made those bonds, we're at the maximum point in the energy pathway. So the transition state is the maximum in energy. So I'll note This is what we mean by bimolecular. There are two molecules in the rate determining step. They have to come together. So let's think about one of the implications of this mechanism in a little bit more detail then. Let's think about the stereochemistry of the process. The nucleophile attacks the electrophile and pushes out the leaving group. And it does this by attacking from behind that carbon-bromine bond. So the OH minus goes in and the Br gets pushed out, just like that. And this means the reaction occurs with some geometric control. Notice in the product, the OH is on the left, and we flipped the C2H5, the CH3, and the H. The CH3 is still coming forward, the H is still going backward, the C2H5 is still on the top, but instead of having the bromine on the right, in the product, we have the OH on the left. This is sometimes referred to as a Walden inversion. We've inverted that carbon atom. And a nice visualization of that, that's sometimes used in textbooks, is it's rather like an umbrella blowing inside out. And so we're converting the stereochemistry. We're pushing this, the umbrella flips the other way round, and we're changing the stereochemistry at this carbon atom. The final bit of this screencast is a you do the work. And it's a relatively simple one. Think about this reaction. Try and draw the product of the following reaction, assuming that it goes by an SN2 mechanism. And if you're a chemist or a biochemist and you've had the courses on stereochemistry with Glenn Hurst, you might want to label the stereochemistry of the product and the starting material using the R and S nomenclature. If you're a natural scientist, you might want to look those terms up. You'll learn more about them when you come back to those concepts in the summer term. But try to draw out the outcome of that SN2 reaction. And I'll see you next time to talk about a different mechanism of nucleophilic substitution. If what I explained in screencast 11 was all there was to nucleophilic substitution, life would be very simple. But in actual fact, experimental chemists realized that some substitutions have very different outcomes. And by considering these, they realized that there was the possibility of another subtly different mechanism. So in some nucleophilic substitution reactions, they found a different rate equation. They found that the rate equals a rate constant times the alkyl halide. And there was no nucleophile in this rate equation, which was surprising. Why would the nucleophile not be involved in controlling the rate of reaction? What that means is the nucleophile is not involved in the rate determining step. And that means a different mechanism must be occurring. So let's have a look at it, and then we'll think about what that mechanism is. So in this case, what happens is the CX bond breaks, essentially spontaneously. There is one molecule in this rate determining step. All on its own, it ionizes and forms a carbocation. And this is not a transition state, it's an intermediate. This is something that could be isolated. It can be more or less stable. And then what happens in a second step of the reaction is that the nucleophile attacks the carbocation and you form a bond between the carbon and the nucleophile. So, how would we describe this mechanism? Well, we'd say it's a substitution. We'd say it's nucleophilic. However, the nucleophile attacks in the second step, not the first slow step of the reaction. So not in the rate determining step. That's why it doesn't appear in the rate equation. And most importantly, as well as being a substitution and being nucleophilic, it's unimolecular. Unimolecular means there is one molecule in the rate determining step. And for these reasons, we call the mechanism SN1, not SN2. SN1 because there is one molecule in the rate determining step. I guarantee that in an exam, some of you will get confused and you will think, oh, this is a two-step process, so it's SN2. No, that's not what the number means. The number 1 means how many molecules are in the rate determining step. One molecule. And this is actually the reaction mechanism that some of you will have learned by rote in A-level. You'll have been told this is how nucleophilic substitutions work. Okay? Now you might think that this mechanism breaks my basic rules, okay? Because we're not finding the negative charge in the first step. But really all the same arrows are occurring, just in a different order, right? We're breaking a weak bond, then we're attacking with a nucleophile from the negative to the positive. And it's worth reflecting on why those arrows are happening in a slightly different order. And there are a couple of reasons. One is the nucleophile is actually not so reactive to attack C delta plus. If that nucleophile is not very reactive, it's not going to go zooming in there like it did in the SN2 mechanism. Or maybe the CX bond is really very weak and easily broken. So maybe the CX bond is so weak it just falls apart before the nucleophile attacks. Both of those factors would change the order of the arrows and favour an SN1 mechanism over an SN2 mechanism. And we'll come back to these ideas in more detail in the next screencast. Now let's think about how the SN1 mechanism leads to some different outcomes. Let's think about the stereochemistry of the process. Let's think about a system where R1, R2, R3 are all different. So we have a chiral molecule here. And what happens in the first step is the leaving group leaves. We have a weak CX bond and it falls off and it generates a carbocation. Carbocations are planar. They're planar and they have an empty p orbital sitting here. I'll even draw that p orbital on. And with that empty p orbital, you could attack with the nucleophile into either side of that empty p orbital. So we'll note the nucleophile can attack from either side. So what happens in those two different outcomes? Well, if it attacks from the left, we make this product with the nucleophile on the left. And if it attacks from the right, we'll make this product with the nucleophile on the right. Notice we're not changing the R1, the R2 and the R3. The R1 is kind of pointing up, the R2 is pointing forwards, and the R3 is pointing backwards in each case. It's just whether the nucleophile has gone on the left or the right. As a general rule, it's always easier for us to draw our mechanisms happening in the plane of the paper with the substituents on the molecule fixed, either going forwards or going backwards. It makes it easier for us to draw. Okay? Now, those are both equally likely. The nucleophile is just as likely to attack from the left as it is from the right. So you'll get 50% of this and 50% of this. And what you'll also notice is these two products are mirror images of one another. We refer to mirror image compounds as enantiomers. And so the fact that the nucleophile can attack from either side, this means we make both enantiomers. And in fact, we make those enantiomers in a 50-50 mix, and we describe that as a racemic mixture. It has both enantiomers in it, and the word to describe that is racemic. And again, these pieces of language like enantiomers, racemic, chirality, those are things that you'll meet in the course with Glenn on stereochemistry. So this reaction, unlike the SN2 reaction, proceeds with loss of stereochemical information, so-called racemization. So in SN2, inverted the stereochemistry and gave us a single enantiomer product. SN1 scrambles the stereochemistry and gives us a 50-50 mixture of the two enantiomeric products. And this is one of the reasons that they knew there was a difference between SN1 mechanisms and SN2 mechanisms. So I have another bit of you do the work for you to go away and think about. This is exactly the same reaction that I wanted you to work out the outcome for the SN2 reaction for in the last screencast. Now work out the outcome with an SN1 reaction. Draw the product, label the product if you can, if you're a chemist or a biochemist, and think about that. It's the kind of thing I'd set in an examination. Okay? Now let's think about the energy profile of this reaction, because it's slightly different to the SN2 reaction process. This time we have our reactants and they overcome an energy barrier to make an intermediate. So here is our activation energy, EA, and we make this reactive intermediate, and the reactive intermediate is a carbocation. And that reactive intermediate then converts rapidly into the products, because what's happening in this second step, this is where the nucleophile attacks. Two steps: make the carbocation, attack it with a nucleophile. And the second step is fast. It has a low energy barrier because the nucleophile really wants to attack the carbocation. This first step is the unimolecular one. It's the loss of leaving group. So the activation barrier is the loss of leaving group. And if we think about this energy profile, we've said this a few times in this course, the more stable the intermediate carbocation, the lower the energy barrier to reaction. The lower the energy barrier to reaction. So if we have a relatively stable, energetically accessible reaction intermediate, then we can make that reaction intermediate more easily, and this reaction will progress faster. So let's look at an example. Here are four different possibilities over the page. And I want you to think which will react fastest in an SN1 reaction. And there's going to be a little test embedded where you can click on what you think the right answer is. Hopefully, you said that the fastest one in an SN1 reaction will be the one on the left. And the slower one will be the one on the right. In each case, we're talking about the X group falling off to generate carbocations. This carbocation is the most stable because it has 3 plus I inductive effects. Those alkyl groups are pushing electron density towards the carbocation, stabilizing it. This one has no plus I effects, so it's the least stable. 0 alkyl groups pushing in. Here we have 1 alkyl group, here we have 2 alkyl groups. So this tertiary, secondary, primary, tertiary is better than secondary, is better than primary, because you're making a more stable carbocation. This is easier to do because this is more energetically accessible. So just a quick note, why are tertiary carbocations more stable than primary carbocations? Well, because they have plus I inductive effects. And we know that also they have this hyperconjugation effect, where the alkyl group is able to stabilize the adjacent carbocation by kind of donating some of its electron density through some not very good bond overlap. Okay? But all those things push electron density in, stabilize the carbocation, and make the process more favorable. So we begin to understand what kind of leaving groups can leave quite easily in an SN1 process. And this is something that we'll come back to in the next screencast. There are some other stabilized intermediates here. We've got stabilized intermediates in which a bromine can leave like this, generate a positive charge here. Why is it stabilized? Well, we can push electron density out of the aromatic ring because the aromatic ring has a plus M mesomeric effect. We talked about that a few screencasts ago, and it helps stabilize this overall process. And then, of course, the nucleophile can attack in the second step and make the product. So this is not inductively stabilized, this is mesomerically stabilized. And we can do the same here, where if the bromine group leaves, it generates a carbocation adjacent to this ether group, and that lone pair of electrons can push electron density like that, generates a resonance form. We could draw the resonance form, and we talked in an earlier screencast about why this is a good resonance form. And then, of course, the nucleophile can attack that nicely stabilized carbocation. So these are bromines that can leave quite easily because they have mesomeric effects stabilizing those carbocations. In the next screencasts, we're going to go on and think a bit more about pi systems, and then we're going to start to think about why would some molecules do SN1 reactions and some molecules do SN2 reactions, and how can you predict that using a set of simple rules to add to my rules of mechanism.